In this video, we are going to study organic chemistry of BSc Part 1 and the chapter's name is aromatic electrophilic substitution. So now let's take up electrophilic attack on benzene nucleus, and the first is pi complex formation. When an electrophile attacks on benzene, then complexes form in between delocalized pi orbitals of benzene and electrophile. It is known as pi complex formation. In this we see that this electrophile forms a bond between the delocalized pi electron cloud system of the benzene and not with any particular carbon atom. So in pi complex, bond is not formed in between electrophile and benzene, that is a regular covalent bond formation between one carbon atom of the benzene ring and electrophile does not take place. It is an exothermic reaction, and if we see the illustration of no bond formation in between carbon atom of the benzene and HCl, it can be explained by the reaction of DCl with toluene. DCl also forms pi complex with the toluene, and we see that the hydrogen of the benzene ring is not replaced by deuterium. Hence, it is found that in pi complex there is no formation of a regular covalent bond between carbon and deuterium. Aromatic hydrocarbons form stable pi complexes with halogens, silver ions and picric acid. These pi complexes are also known as charge transfer complexes. Now we come to another type of complexes. It is seen that when an electrophile reacts with benzene in the presence of Lewis acids like AlCl3 or BF3, it forms another type of complex known as sigma complex. So when DCl reacts with benzene ring in the presence of AlCl3, then the hydrogen atom of the benzene ring is rapidly replaced by D, and the complex thus formed is sigma complex. These complexes are also known as valent intermediates. In this, D plus forms a covalent bond with carbon atom of the benzene ring, and the positive charge of the D plus is distributed over pi orbitals of the 5 carbon atoms. So if we see the reaction of benzene with DCl in the presence of AlCl3, then we see that the electron pair between the D and Cl shifts on the Cl, making it negative, and D becomes positive. And also here the bond pair between the carbon 1 and carbon 2 moves out of the ring and forms a bond with the D, and the numbers 2 carbon attaches becomes positive, and by continuous sharing or successive sharing of the electron pair between different carbons, the positive charge migrates within the ring from second carbon to the fourth carbon to the sixth carbon, and these are known as resonating structures, and this is the hybrid of these resonating structures, and it is called an arrhenium ion. Now if we see the general mechanism of electrophile then substitution reactions, we see that aromatic hydrocarbons are generally known as arenes, and if one hydrogen atom is removed from one arene, then aryl group is formed. Aryl group is represented by Ar, and arene is represented by ARH. Arenes show characteristic electrophilic substitution reactions. So if we see the general electrophilic substitution reaction, then we see that this benzene reacting with electrophile. Now this hydrogen which is at carbon 1 gets replaced by electrophile, and the number 1 carbon's hydrogen is lost as proton. Or if we see here ARH, this H is replaced by E, it is lost as proton, and this E gets bonded with AR. Halogenation, nitration, sulfonation, alkylation and acylation are certain examples of electrophilic substitution reactions. Now we come to the mechanism. There are 6 delocalized pi electrons present in benzene ring. These electrons act as electron-rich source or nucleophilic center. They rapidly react with electrophile. These 6 pi electrons are present in the benzene ring in a closed shell. There are 3 steps which are used in electrophilic substitution reaction. The first step is formation of electrophile. Now this can happen in 2 ways. In the first, the reacting species, that is the attacking species, which is made up of 2 parts, electrophilic and nucleophilic part, splits into electrophile and nucleophile. Or in the another way, this attacking species reacts with Lewis acid, whereby the nucleophilic part gets abstracted by the Lewis acid to form an adduct, and this electrophile is released. The second step is formation of intermediate carbonium ion or carbocation or arrhenium ion as we say it. So we see that electrophile formed in first step attacks pi electron cloud of benzene ring and forms bond with carbon atom of the ring. This carbon atom which is attacked and now bonded with the electrophilic converts from sp2 hybridized state to sp3 hybridized state, and the 2 pi electrons are used up in bonding with the D, that is the electrophile, and the remaining 4 pi electrons are delocalized and form non-aromatic carbocation. These carbocations are known as benzenium ion or sigma complex or valence intermediate or iridium. So as we saw before, the electrophilic attack renders sp2 carbon sp2 hybridized carbon to sp3 hybridized carbon and number 2 as positively charged, and this positive charge on the carbon shifts within the ring from 2 to 4 to 6 position, and these resonating structures, now this is represented as hybrid or aluminum ion. So first is benzene, second, third and fourth are resonating structures, and the fifth and the sixth are known as aluminum ion or carbocation. Now we come to the third step. Aluminum ion formed in second step loses the proton, and the 2 electrons which bind the hydrogen get into the pi system of the benzene ring, and carbon attacked by and bonded to the electrophile attains the sp2 hybridized state from sp3 of the intermediate, and aromaticity is retained, and we get the product, and this hydrogen is lost as a proton. So if we see the energy profile diagram, we see that here in this is the reaction coordinate, and this is the potential energy axis. So here we see that if we see on the potential energy axis, the energy of the reactant is the in between, or it is higher than the product, but in between the energy of the reactant and the product there are 2 humps and 1 valley. These 2 humps represent transition state 1 and transition state 2, and this hump represents the intermediate or the valence intermediate. So we see that the benzene reacts with electrophile and forms transition state 1, which is of the highest energy. This transition state 1 converts to the intermediate, and this intermediate is of the lower value than the TS1, and this rearranges to give the transition state 2, and this transition state 2 then gives rise to products which is at the lowest potential energy level of the diagram. So this is a exothermic diagram. Now we come to energy profile diagram. In electrophile substitution reaction, the aluminum ion is on intermediate. In potential energy diagram, it is in between 2 transition states. From the diagram we can see that the energy of activation energy is more than the energy of activation of the second. So energy activation first is greater than the energy of activation 2, and the activation energy 1 is the energy of the activation for the formation of aluminum ion, and activation energy 2 is the energy of activation for the formation and product from aluminum ion via intermediate. In the first process, when aluminum ion is formed, then benzene is endothermic process, or as stable benzene structure breaks. Now the product formation process is exothermic, as benzene ring again attains stability. So the formation of aluminum ion is the rate determining step, while elimination of proton is a first step. So this is all for today. Thank you.